continuous functions. As a starting point, we have the following theorem. Let A be a subset of the real, and let f, g be functions on A, which is a subset of R. And let's suppose that B is some real number. Suppose that C is in A and F, G are continuous at C. Then two things hold: F plus G, F minus G, F times G, and the constant times the function F are all continuous at C. Also, if H is a function between the reals and between A and the real, which is continuous at C, which is in A, and h of x is not 0 for all x in A, then the quotient f over h as a function is also continuous at C. Now the proof is fairly simple, and because the proof is essentially repetitive for all cases, I will just look at partly part A. So assume that F and G are continuous at C, then the limit of f of x when x is approaching C is equal to f of C, and clearly the limit of g of x as x is approaching C is equal to g of C. Thus we know that f of C plus g of C will be equal to the limit of f of x plus g of x as x is approaching C by the rules for limit of functions. And again, all the other cases are similar, and their proofs are left as exercises, which is worth noting is the following. Let us suppose that A is a subset of the real, and let f and g be continuous function. On A, and let's suppose that B is some real numbers. First, the functions f plus g, f minus g, f times g are continuous on A, and B if H is a map from A to R which is continuous on A, and h of x is not 0 for all x in A, then the quotient function f over h is continuous on A. And a direct application of this theorem is the following corollary: all polynomials functions and all rational functions are continuous on their domain. Example: suppose that let f of x be x squared plus 1 over x power 4 minus 1. Notice that x power 4 minus 1 can be rewritten as x squared minus 1 times x plus 1, x squared plus 1, and as such, thus the domain of f is the set of all real numbers such that x is not 1 and x is not -1. So we can regard the domain of f as -infinity to -1 union -1 to 1 union 1 to infinity, and let's call this set here A. And then clearly, since f is a rational function, then f is continuous on all of A. The sine function is continuous on the set of all real numbers. And to prove this theorem, I will need a lemma. So let me start with the following lemma. For any xy which is a real number, it turns out that sine of x minus sine of y, that's equal to 2 sine of x minus y over 2 times cosine of x over 2 minus y over 2. So let me first prove this lemma, and this lemma is very computational. So given xy which are real numbers, first note that sine of x over 2 minus y over 2 using one of the property of the sine function is sine of x over 2 times cosine of y over 2 minus cosine this is supposed to be plus, sorry. Alright. Okay, so sine of x over 2 minus y over 2 is equal to sine of x over 2 cosine over 2 minus cosine of x over 2 times sine of y over 2, and cosine of x over 2 plus y over 2 is equal to cosine of x over 2 times cosine of y over 2 minus sine of x over 2 times sine of y over 2. Now taking the product, cosine of x over 2 minus y over 2 time sine of x over 2 minus y over 2 time cosine of x over 2 plus y over 2 gives the following: sine of x over 2 cosine of y over 2, put a negative there, sine of x over 2 sine of y over 2. Let me start this all over, sorry. So instead it's sine of x over 2 time cosine of y over 2 time cosine of x over 2 time cosine of y over 2 minus sine of x over 2 cosine of y over 2 sine of x over 2 sine of y over 2 minus cosine of x over 2 sine of y over 2 time cosine of x over 2 cosine of y over 2 plus cosine of x over 2 sine of y over 2 sine of x over 2 sine of y over 2. Alright, now let's put these terms together. If we put these two terms together with this one and that one and this one, the following as well as the following, we recall that cosine, sine of 2 alpha is equal to 2 sine of alpha times cosine of alpha. So using this trig identity, then this will becomes 1/2 sine of x times cosine square of y over 2 minus 1/2 sine of y times sine square of x over 2 minus 1/2 sine of y cosine square of x over 2 plus 1/2 sine of x over 2 sine of x times sine square of y over 2. Alright, now I will collect the following, this and this one, a term, and then I will collect this term together with this term here. Let me actually put them all off together, this one and this and that. Alright, so collecting those terms, then it's clear that we obtain 1/2 sine of x time cosine square of y over 2 plus sine square of y over 2 plus minus 1/2 sine of y time sine square of x over 2 plus cosine square of x over 2. And the point here is the next point that I'm about to make is that by the Pythagorean theorem, this is 1, right? So those two are equal to 1, and as a result we obtain 1/2 sine of x minus 1/2 sine of y. Now multiplying this equality by 2 gives that sine of x minus sine of y is twice of sine of x minus y over 2 time cosine of x plus y over 2. And this proves the lemma. So we want to show that given x and c, which are real numbers, and if we let epsilon be a positive number, there exists delta which is positive, such that if the distance between x and c is less than delta, which often depends on epsilon, then the distance between sine of x and sine of c can be made less than epsilon. Right, so let's look at the distance between sine of x and sine of c. Well, from our previous lemma, from the lemma above, we see that sine of x, absolute value of sine of x minus sine of c, is going to be equal to the absolute value of 2 sine of x minus c over 2 times cosine of x plus c over 2, and this is 2 times the absolute value of sine of x minus c over 2 times the absolute value of cosine of x minus c over 2, and this thing here is always less or equal to 1, so this product will be less than 2 times sine of absolute value of x minus c over 2. And another useful result is the following: for any theta, which is a real number, sine of theta is let's say the absolute value of sine of theta is less or equal to the absolute value of theta. All right, so suppose we have this at our disposal, and we will use this result. Suppose we believe these results, then it becomes true that this will be less than 2 times the absolute value of x minus c over 2, which is just the absolute value of x minus c. All right, so now I would like to replace this with for every epsilon. Yeah. Now, so let's epsilon be greater than 0, should I say, given epsilon, which is greater than 0, let delta be equal to epsilon, and assume that the distance between x and c is less than delta. Then automatically the distance between sine of x and sine of c is less or equal to the absolute value of x minus c, which is less than delta, which we set to be equal to epsilon. Therefore, f is a continuous sine is a continuous at c, and since c is arbitrarily chosen, then we can then conclude that sine is continuous on every real numbers. It's continuous on all r. Next, we'll prove that cosine is a continuous function, and to this end we'll use a similar idea. So we use the fact that we already have an identity at our disposal, and I would like you to pause here and to verify this identity for yourself. Okay, and once you verify this identity, then you may proceed. So then for c, we'll have that the distance between cosine of x and cosine of c will be twice of the absolute value of sine of x plus c over 2 times the absolute value of sine of x minus c over 2. So next, then since we know that sine of x plus c over 2, its absolute value is always less or equal to 1, using these this bound, then we know that the distance between cosine of x and cosine of c will be twice of the absolute value of sine of x minus c over 2. And then using again the fact that the absolute value of sine of theta is always less or equal to the absolute value of theta, then we get that sine of sine of x minus c over 2, absolute value of this, will be less or equal to x minus c, absolute value of x minus c over 2. So in summary, we get that the distance between cosine of x and cosine of c is less or equal to the distance between x and c. And for any epsilon which is greater than 0, I will let delta be epsilon. And assuming that the distance between x and c is less than delta, then it follows automatically that the distance between cosine of x and cosine of c is less than epsilon. Therefore, cosine is continuous at c. The product rule by the product and quotient rules, secant, cosecant, tangent, cotangent are all continuous on the domains. Also, the following claim is worth noting. If f is a function between a and r, where a is a subset of the reals, if f is continuous on a, then the absolute value of f is continuous on a as well. Okay, and the proof is similar to it's very similar to things that we've done in the past. So assume that f is continuous on a. Let epsilon be a positive number, and suppose that c is an element of a. Then by assumption there exists delta, which is a positive number, such that if the distance between x and c is less than delta, then the distance between f of x and f of c will be less than epsilon. So fixing delta, which is positive as described, and assuming that the distance between x and c is less than delta, then we obtain that the distance between f of x, the absolute value of f of x, and the absolute value of f of c is less or equal to the distance between f of x and f of c by a corollary of the triangular inequality. Of the triangle inequality, and by assumption this is less than epsilon. The next theorem deals with composition of continuous function, and the theorem is stated as follows. Let a and b be two subsets of the real lines, and let f be a map taking a into R, and G is mapping B into R. Okay, and suppose that the range of f, which is f of a, is contained in B, which is the domain of G. If f is continuous at a, at a point C, if f is a continuous function at a point C, which is in the domain of f, a, and if G is continuous at B, which is f of C, in the range of f, but in the domain of G, then automatically the composition function G composed with f, which is mapping A into the real line, is continuous at C. We want to show that for every epsilon which is greater than 0, there exists a delta which is positive, such that if the distance between x and C is less than delta, then the distance between f of g of x and f of g of C is less than epsilon. And I will encourage you to refer to the diagram which I drew earlier to follow the stream of ideas that I will be presenting. So let W be an epsilon neighborhood of G of B, where epsilon is arbitrarily selected. Since G is continuous at B, little b, then there exists a delta neighborhood V of B, which is f of C, such that if little y is in B intersect V, then automatically G of y is in W. Now, since f is continuous at C, there exists a gamma neighborhood U of C, such that if little x is in A intersect U, then automatically f of x is in V. So x is in A intersect U, then f of x is automatically in B intersect V. So G of f of x, which is G composed with f at x, is in W. So here is again an illustration before I complete this proof. This is f, and then G, and we have A here, and B, and then C, big C, And suppose C is an element here, and we map C to f of C, which we call B, and then G will map B to G of B. Okay, and we want to show that for any epsilon which is positive, there exists a delta which is greater than 0 and depend on epsilon, such that if the distance between x and c is less than delta, then the distance between f of g of x and f of g of c will be less than epsilon. So we start by selecting a neighborhood, a delta, an epsilon neighborhood around g of b. Right, so this is W, which is a V epsilon of G of B. And then since G is continuous, then we can find a neighborhood around little b, which is f of c, and we call this neighborhood V. Let me put it in green. So I can find this neighborhood by the continuity of G. You can find this neighborhood around f of c, and we call this V, and this will be some V delta of little b, such that as long as you pick any x here, if you select any little x here, then automatically you know that G of x will be in this in the epsilon neighborhood of G of B. Now, since f is continuous, then picking a neighborhood around f of c, I can find a neighborhood around c, and we call it U. Let me use orange, so I can find this neighborhood around C, which is we call this neighborhood U, and U is a gamma neighborhood around C, such that if you pick any say if you pick any, let's say, A in here, then automatically you will guarantee that f of A will be in V delta B. Okay, so now so given x here now, then we know that f of x has to be in V delta B, and again by construction, the image of f of x under G, which is G of f of x, has to be in the epsilon neighborhood of G of B. So indeed, if you give me any G of B, which for us here G of B is really just G of f of c, and I can and you give me some epsilon neighborhood, that's this is what I mean. If you give me some epsilon neighborhood around G of f of c, I can find a gamma neighborhood around C, such that if x is inside this neighborhood, this gamma neighborhood of C, then automatically G of f of c will be inside the epsilon neighborhood of G of B. All right. Let's f be a non-negative and a continuous function on A. Okay, then I claim that square root of f is continuous on A, And the proof is fairly simple. We will accept for a fact that the square root function is continuous on its domain, and then if we look at this map, so f is mapping a into the positives including 0, and the square root function, let's call it s. So by s I mean the function s of such that s of x is equal to square root of x. This function is taking the positives including zeros, the non-negatives, into the non-negatives, right? And then this map, which is s composed with f, is the square root of f. And by the composition of continuous functions, it is clear that square root of f is continuous on A. Again, we are taking for granted here that s is continuous on its domain, the square root function. All right, so clearly this proof hinges upon the fact that given s, which is mapping the non-negatives into the non-negatives, such that s of x is equal to square root of x, then s is continuous. And I will leave the proof here as an exercise. And by this, I would like you to pause the video and write this proof for yourself. And in fact, as a hint, I would say that you should use sequences. And theorem 3.2.10 from Bartle in our textbook. Okay, so I would like to conclude this lecture by making the following comments. The preservation of continuity through composition of functions provides new classes of continuous functions. And the conclusion of section 5.2, which is on combinations of continuous function, is that all polynomials, all rationals, all trigonometric, all exponentials, log functions, and all algebraic operations and composition of these functions will represent continuous functions on their domain. Right, so then this gives us a fairly large class of functions to play with, and we will call these nice class of functions, we'll call them elementary functions. Thank you.